With this work, we explore different aspects of visualization design and how we effectively visualize data in AR and VR. In information visualization, graphical perception gets at how well a visualization represents the data to the user. And this can be done through a number of visual channels, such as color, size, and height, that represent the columns of your data. And there's been a lot of research in graphical perception on 2D displays, perhaps most notably by Cleveland and McGill, to establish how well different visual channels depict data to the user. With their work, they conducted an empirical study looking to rank these different visual channels for how accurately they represented data to the user. And this is important because when done well, information visualizations can help people toward understanding the data and drawing conclusions. These are a couple examples of relevant visualizations that paint a fairly clear picture of the delegate counts for the Democratic primaries on the left and the spread of the coronavirus on the right. On the flip side, if you make strange choices like truncating your axes to not start at 0, or if you use unintuitive color scales in your visualization design, you can actually wind up deceiving your viewers. And everything we know about how people accurately read visualizations is grounded in 2D. We don't know how well these ideas hold in virtual and augmented reality. So we look at how this issue of graphical perception changes as we move from standard 2D displays to VR and AR. So to tackle this issue of graphical perception in immersive analytics, I'll discuss the motivation, execution, and results of a visualization study that we ran. First, getting into the motivation. Prior research on immersive analytics has identified benefits to using AR and VR for data visualization. These include, but aren't limited to, sense making across tables, use of spatiotemporal data, and use of high-dimensional data. However, there are some instances where we can deceive viewers just by using 3D in our visualizations. For example, the purple region looks a lot larger than the red one, and the green region looks much larger than the blue one when this pie chart is projected in 3D. But in fact, those aren't the conclusions you should be drawing based on the underlying data. And in a lot of cases, the use of 3D gives certain data points more screen space and can even wind up hiding data points. So while some people are encouraged by the use of AR and VR for 3D data visualization, others are turned off to the notion altogether, as 3D data visualizations have a history of being poorly designed. So toward trying to reconcile that 3D visualizations have been so ineffective in the past, with findings that using AR and VR can help, we ran an empirical study to figure out what good visualization design looks like in immersive AR and VR. And in doing that, we consider 3 goals for designing visualizations: for users to get the right answer, to read the visualization quickly, and to be engaged with the data. And again, while this has been studied quite a bit for 2D displays, relatively little work has explored graphical perception in immersive AR and VR displays. So with our work, we wanted to see how does the perception of data visualizations change as we consider immersive AR and VR displays. And quickly revisiting Cleveland and McGill's work on graphical perception, we took a similar approach of exploring visual channels, considering 5 of the channels that they studied: position, length, direction, volume, and color, and how effective they are in immersive environments. We ran a 3x8 by 3x2 mixed factors study with display type distributed between our 42 participants and all other factors within participants. Our aim was to get at these differences in visualization perception for different immersive displays, considering several visualization designs and tasks. So first we looked at 3 different display types. The desktop condition allowed participants to look at visualizations on a 2D monitor. In the VR condition, we used an HTC Vive, and the AR condition also used the HTC Vive with an attached Z Mini for pass-through AR. The user interface for selection in AR and VR was to use a gaze raycasted cursor, much like the HoloLens, for specifying an object, and the trigger on the back of the remote for selection. The desktop interface uses standard interactions from 3D modeling for panning and rotating the viewpoint and selecting points with the mouse. So since interaction standards are different for AR and VR displays than for desktop displays, we rely on previous literature that a gaze-based selection interface provides at least a reasonably comparable performance to a mouse interface when we design for selection on the Vive. We also considered different visualization designs. And as I talked about before, we explored 5 different visual channels, which are ways of representing data columns. So we showed participants a number of different visualizations that had X, Y, and a third dimension in this case encoded with color, or with a Z dimension and a fourth dimension for color. Other visualizations use size to encode data, some use orientation of lines, and we also tested bar charts that use height to encode data, and scatter plots that use depth, where the further along the Z-axis, the greater the value. So these are the visualization types that we used in our study, and to avoid confusion, I'll draw attention to the fact that when I discuss 3D visualizations, those are the X, Y, and third dimension, whereas 4D visualization use X, Y, Z, and a fourth dimension. Participants engaged with 3 different tasks. In an extrema task, participants look for the highest or lowest individual data point. Quadrant means tasks ask participants to identify the largest or smallest average area in a visualization, and trend tasks ask participants to identify the overall trend in the data. And for symmetry, half of the tasks asked for the highest value, highest area, or increasing trend, while half asked for the lowest value, area, or decreasing trend. So with display type distributed between participants and all other variables within participants, participants saw a total of 48 trials in the study. Here's a quick snippet of what participants saw in the AR condition. So participants would see a text describing the channel, dimensionality, and task for the next trial, and then the visualization loads in the room. Participants can navigate around the room before selecting and confirming their answer. Selecting No for a mistaken selection allows participants to return to the visualization to select the intended point or region, and selecting Yes automatically loads the next trial. Participants in the desktop condition had the same tasks, with the only difference being in the navigation interface. So as with the AR and VR conditions, participants can navigate to different perspectives around the visualization before confirming their selection. We took several measures, both objective and subjective. We were primarily interested in error and time to completion for each trial, but we were also interested in how much participants navigated the environment, measured as the positional and rotational displacement of the camera game object at each frame. In between each block, we collected measures on how much participants preferred each visualization type through Likert scale questions. And after all 3 blocks, there was a final questionnaire with more Likert scale questions and open feedback. So with this study, we had 4 hypotheses that we wanted to test. First, we anticipated that participants would be able to identify differences in size for all displays, but that when asked to disentangle size and depth in the same visualization, participants in the desktop condition would struggle. We anticipated that stereo viewing in AR and VR should help participants identify whether a point renders small because the size of the point is small, or because that point is far away. We also anticipated that participants on the desktop and in VR would be able to distinguish differences in color reasonably well, but that participants in AR would struggle identifying those color differences against a non-constant backdrop. Third, we expected the effectiveness of the navigation interface would correlate to performance with depth, height, and 4D visualizations, which all require some amount of navigation. And lastly, we expect a subjective preference toward embodied navigation over the mouse and keyboard. We have a more complete report of the results in our paper, but for this talk I'll just focus on the hypotheses and key findings. So generally we wanted to see if there were differences in our measures across displays, and we did find there to be significant ones. Revisiting our original hypotheses, we first thought that participants would have difficulty disentangling depth and size on the desktop, and we saw strong evidence in support of this that participants struggled with 4D size visualizations on the desktop, but that accuracy wasn't really compromised with depth visualizations. Subjective feedback pointed to the fact that participants on the desktop were able to navigate to a perspective on the side of the visualization to identify differences in depth. However, participants clearly had difficulty when asked to disentangle size from depth in 4D size visualizations on the desktop. Stereo viewing in AR and VR resolves this issue, allowing participants to infer depth without necessarily rotating the viewpoint. Second, we thought that color-based visualizations would be challenging in AR, and we found that to be the case as well. We found that participants were typically less accurate and slower in AR than on the desktop and for VR. And we anticipate that this was likely due to the non-constant background, as participants specifically called out that color in AR was particularly difficult due to the interference from the background color of the room. And here's an example of this using color in AR and what it would look like in VR or on the desktop. You can clearly see the interference from the background of the room. And this not only has implications for use of color in AR, but also begs the question of whether use of skyboxes in immersive visualization impacts performance. So here you can see visualizations as the participants saw them in VR, and how they would have looked with default skybox and lighting conditions in Unity. For color visualizations in particular, in the bottom left you can see that the skybox makes it almost impossible to distinguish differences in color, because the white and blue backdrop makes points appear darker than they actually are. You can also see on the bottom right that white data points can get washed out entirely. We anticipated that success with the navigation system would correlate to performance for depth, height, and 4D visualizations. We saw some evidence toward this, as despite comparable accuracy, participants were slower in the desktop condition for 3D visualizations that require navigation. Accuracy didn't seem to be compromised, as there's generally a good perspective when assessing height and depth, but it just took longer for participants to navigate there. We saw only a little evidence toward preference to the embodied navigation, with participants reporting higher scores for the intuitiveness of inferring depth in AR and VR than on the desktop, despite no significant difference in ease of navigation. In open feedback, participants described walking into the graphs and being able to point with their fingers as being helpful techniques for VR and AR navigation. And most participants responded positively to the desktop navigation interface, though there were some that pointed out tasks that were particularly challenging with the mouse and keyboard interface. I touched on differences in navigation across displays, but one thing that was not a part of our hypotheses, but was immediately apparent, was that people navigated much more in AR than in VR. Here we normalized for time to completion, as we didn't want to confound large amount of navigation with high time to completion, and we found that participants moved around and looked around much more in AR, perhaps indicating greater comfort and more willingness to engage with visualizations when in augmented reality. So a couple additional pieces that we touched on with our study, but that would benefit from future work. We could consider a number of color ramps that use different start and end colors, as well as diverging ramps that go through a neutral color. Additionally, we only tested in one room, and considering that participants performed poorly with color in AR specifically, it's worth considering the target environment when designing color visualizations in augmented reality. We would also like to further explore the effect of display type on navigation strategy, as we focus mostly on amount of navigation with this study. Understanding how participants like to move around in different environments could impact how we should design visualizations depending on the display type. So with further study, we may find that different display types are better suited to different visualization types. Based on the finding that people are more willing to navigate in AR than in VR, we might find that higher dimensional data is better displayed in VR, whereas AR displays may be better suited to smaller, situated visualizations. With our empirical study of how visualization perception changes for different display types and dimensionalities, we've identified key differences that should inform future immersive visualization design. Most notably, we found that color perception was worse in AR than in other conditions, that differences in size were difficult to disentangle from differences in depth on desktop displays, and that participants were more comfortable navigating in AR than in VR or on the desktop. So with that, I'll thank you for your time and take questions.